The memory stick that I stored this on, I worked out on the train down, had a capacity of about 5 billion words. So you get some idea of the theme that I'm talking about tonight. Telling tales of colonial times in Kenya. But I'm rather fond of this quote because it sums up my career. I've spent rather a lot of time working on forecasting, for instance, time series econometrics, and spent a great deal of time trying to forecast the future, particularly in industry. But actually the most taxing thing is writing the history of technology, which is what I've been doing far more recently. So I've certainly given my mind much work and trouble trying to secure the past, and that's what I want to talk about tonight. Okay. David Edgerton, who was probably known to many of you, is a prolific writer and will be mentioned later on. A prolific writer, for instance, reinterpreting the 20th century view of warfare, came out with this statement in Technology and Culture, which is, after all, in some sense, a rival magazine to our own journal, although I don't think it's anywhere near as good these days. In the history of technology, analysis of what historians have argued, produced, established, assumed, and concluded is extraordinarily rare, whether in celebratory, as tonight, or in critical mode. In other words, we don't do enough navel gazing. We don't ask ourselves, what are we actually trying to do when we're writing the history of technology? And reflecting on this, it occurred to me that I didn't actually do that. But I got drawn into the history of technology, largely because of my work, most recently at the University of Manchester, where I was working on innovation research and the management of technology, on things like how should R&D programs be conducted, on current issues about technology policy. And I found, particularly when teaching MSc students, that the history of technology very much informed innovation research and the management of technology. In other words, the history of technology was exceptionally useful in a business school because we have this relentless fund of case studies which could illuminate almost anything that the fashionable commentariat had come up with. So it gave you valuable ammunition and a fully loaded ammunition locker to have a go at current problems. And that will become apparent in some of what I have to say. But it also occurred to me, in the light of Edgerton's question, that a lot of the ideas from innovation research, could also shed light on the way that we conduct the history of technology. The one that I'm going to focus on tonight is the ideas of evolutionary thinking, and in particular evolutionary economics. Those who've read the Bloodhound paper would have heard me talking about the notions of communities of practice, and I've also written elsewhere on natural experiments in innovation, whereby you have two teams doing research work on an identical problem, but the two teams are organised in quite different ways, and one succeeds and the other fails. And that's a very interesting piece of a natural experiment. And more recently, I've written in the journal about technology transfer and how technology transfer takes place, and how much scope in particular there might be for the people who adopt the technology to shape it to their own particular needs. But what I want to do tonight is to be controversial and focus here on evolution. I appreciate this will upset the historians in the room, because what I'm actually coming up with is some kind of attempt at an all-embracing explanation, which is precisely the sort of things that historians dislike. And I'm looking forward to hearing Frank's comments on it. So what I'm going to do is to try and apply a universal framework, the theory of evolution, to the history of technology and to see what kind of insights and mileage it gives us, both about the history and also about technology policy if time permits. Now, evolutionary ideas are really just a metaphor. I don't mean evolutionary ideas from biology, but evolutionary ideas in principle, which have been widely applied across a range of disciplines. And evolutionary ideas are a metaphor, and as Stan Metcalf gave a paper at the International Congress on the History of Science, Technology and Medicine, some of you in this room were here in Manchester almost 10 years ago, he gave a paper there to the Newcomen Symposium that we ran as part of that international conference on restless capitalism. And one of the things he said is evolutionary ideas frame our understanding of the processes generating innovation, and then I put in italics, limiting innovation. Because what I hope to persuade you tonight is that evolutionary ideas not only help us explain how ideas develop and spread, but also why they stop happening, why innovation stops happening, why certain industries, the paper industry at the moment, or the steel industry, get locked in to their current technology, and we actually see remarkably little change. So I'm going to talk about not just the life of technology, I'm going to talk about the fact that it doesn't improve, and also I'm going to talk about extinction, because extinction is, of course, central to the idea of evolution. So what I want to do is map out what we mean by evolutionary ideas in the context of innovation and the history of technology. I'm going to give you lots of lovely pictures, of which I have the copyright, showing you 130 years history of the wide strip mill steel, which has given me, should I say, a great deal of work and trouble over the past couple of decades with my colleague, Professor Ranieri. I'm going to briefly mention biological analogies, but I'm going to focus on a thinker that you probably haven't heard of, Lamarck. You probably haven't heard of him because he's French. I bet you all thought that Charles Darwin started it off. Nonsense. Okay, I'm going to introduce some criticisms of the evolutionary approach, which I think are very reasonable. I'm going to say something about the role of the entrepreneur. Two entrepreneurs in particular are going to figure very highly in my account tonight, Townsend and Norgal. And then, if time permits, which it probably won't, I'm going to talk about policy lessons and say something about a rather strange piece of work on innovation that I've looked at, fighting wildfires with the Royal Society. Okay, this then led me to the task, how we sum up evolutionary ideas in 5 concepts. Well, the first and most obvious principle that all of you here would recognize are the notions of variation and selection. The idea that within a market economy, rival firms are all striving to produce new goods that are better, more desirable, more sexy, more attractive, better advertised than that of their competitors. That implies, of course, that if there's variation, some will win out when they get selected by the market or by government, and many will lose out. And this is very obvious. And so although I will keep on referring to it, I needn't labour it at this point. You can quickly draw up a list. 120 years ago, it wasn't clear whether the car would be steam or electric, and only an outside chance that it would have been an internal combustion engine, and indeed, of course, now there's talk that it would be electric. The aeroplane shows enormous variety and 1 or 2 false starts and dead ends. I'm delighted that that Fred Starr is doing a paper on Concorde, which is a classic example of variety and failure and extinction. And we could talk about submarines where there was even attempts with the Calamity class fleet submarines to develop steam propulsion. So I think I've made the point that variety and selection has been a feature of technology for the past couple of 100 years. But I want to introduce some new ideas which are common currency in the management literature, but not common currency in the history of technology literature. So my second principle about evolution is the idea of search, which is related to the behavioral economists, people like Herbert Simon at Carnegie Mellon, and people like Dick Nelson and Sid Winter, who get a name check at the end for writing their book on the evolution of technology. Crises often prompt a search for a solution. All sorts of searches take place, but there's nothing like a good crisis to get things moving. For example, the crisis of climate change is leading to solutions to replace thermal power stations. You can no longer see these magnificent cooling towers with at Edgerton, just off the M62. Why? Because our concern about CO2 emissions has knocked coal generation almost on the head. I think there are perhaps 3 thermal power stations working in England. Whisper it quietly, they're working extremely hard. I see them regularly, and even dear old Drax is burning coal as well as wood, controversially, wood chip. So we're searching for a solution at the moment for alternatives to thermal generation. We're searching for new designs of grid. We're searching for new pricing solutions. We're searching for ways in which we can encourage households to conserve. And that leads me on beautifully to the third point, is that although as historians of technology we focus on technical solutions, we also have to recognise that this often brings along with it new ways of business. Tesla selling cars through the web, for example, new forms of organisation to supply that technology, and new types of competition. We have a delightful example in a recent Newcomen paper, which is Martin Gregory's paper on superseding the seamstress. He not only explains how the domestic sewing machine developed, he also makes the point that it brought new forms of business. For example, patent pools between the 4 or so leading suppliers of sewing machines, the advent of hire purchase to enable people to buy them and in particular earn a living whilst using the machine to pay for it. Notions of part exchange, whereby you could trade in the old models to the new model, and novel marketing techniques. For example, having beautifully dressed ladies demonstrating the latest sewing techniques in showrooms in downtown New York. This goes to show that as a technology evolves, it not only evolves in technical terms, in engineering terms, it also evolves in terms of business organisation, that the two are closely knit. And that's something which this paper beautifully captures. And indeed, I could also give you but also thanks to the ideas of his wife, was a genius at marketing and selling to the new emerging middle classes, opening showrooms in London. He was a genius at logistics. He was one of the key movers behind canal construction and so on. So we're making the point that evolution is the co-development of technology and business ideas. A perhaps less obvious idea is this idea that evolution is an emergent process and you frankly haven't got a clue what's going to happen next. Because ideas change as they spread, they adapt, and the whole system responds by shifting resources. As a result, you get quite unforeseen outcomes, unforeseen structures, and unforeseen ideas developing maybe 5-10 years down the line, where the impetus has been the shift in technology, but actually what is happening is out of control. It's out of the hands of the people that often came up with the idea. I've written about the development of Bloodhound too. The reason that I was interested in this is because this was a massive shift from analog control to digital control of a device. But when interviewing the people concerned, Maurice Gribble and Derek Whitehead and people like that, all the participants at the time, it was quite clear that when they got the contract for Bloodhound 2 control system at Ferranti Automation, they had no idea that it would emerge as a digitally controlled process. The problem you may recall from that paper is that the radar dish in the front of the missile has to lock onto the target within a fraction of a second once the missile has been launched. You have to lock this rotating aerial, you have to lock it for takeoff because there's so many G's involved, but once it gets going, you've got to unlock it and pick up the reflection of the radar bouncing back through bouncing back from the target aircraft to the front of the missile. That calculation to point the radar dish in space, the right elevation, and the right direction, is very complicated in the sense, it is after all rocket science, in the sense that it has to be accurate. We've only got 1 degree of sky. And the people who designed Bloodhound 1 realised that the analog system that they were then using was nowhere near enough accurate enough. So a solution emerged because Maurice Gribble was designing a digital computer, like you do. Maurice Gribble was a very unassuming man, and he thought it perfectly natural that he would sit down one day and design a digital computer. After all, they were used to analog circuits, why not? So that's a classic example of emergence within one company. But you can see across the economy that once a technology starts getting going on its trajectory, who knows what's going to happen next? The final idea, I love this idea because it's the idea of creative destruction. That in order to make things, you have to break things. You have to destroy the thermal power stations to give the space for the wind turbines, for the solar panels and so on. The amusing part about it is that often espoused by neoliberal conservatives in a casual throwaway manner, saying, oh, well, it doesn't matter if communities are harmed by the closure of coal mining, this is just creative destruction. Of course, what they don't realise is that at its heart, it was part of Karl Marx's and Friedrich Engels' thinking. They recognised that capitalism was prone to these phases of creative destruction, whether it was because of war or the decline of capitalist profits. And I find it incredibly ironic that the right wing has picked up such an extremely radical left-wing idea. But the point that I want to make is, setting aside any interest in politics, is that the economic environment is always changing, and as a result, there is a lot of extinction. Extinction is fundamental to the evolutionary process. These are the blast furnaces. I'm sorry that this bottom panel is not telling you that this is carry number 7, carry number 9 at the Monongahela Valley. It is literally an old US steel blast furnace, as you can see, overgrown with trees and falling into dereliction. In this case, I think, in this case, because of the onslaught of the US mini mills, which emerged during the 1990s, making steel very cheaply from scrap in a way that these large, obsolete, integrated works in the middle of Pennsylvania could not compete. Okay, let's make some final observations before we wrap up this section. The first is to emphasize that if you believe in the importance of variety and selection, this also implies failure by lots of people and extinction. So it is the natural nature of things that old technologies pass and get replaced by new technologies. The second point that I'm going to surprise you with is that radical pursuit of novelty is surprisingly novel. Most older technologies are retained. I promised to name check David Edgerton. And his book, The Shock of the Old, does at least make a very neat point that when you look at the world at large, particularly developing economies, as we used to call them, there are a lot of long-established technologies, whether it's battleships and corrugated iron, that are still in widespread use and doing a very satisfactory job. Indeed, the example I'm just about to look at shows a technology that's in some sense been frozen in time for about 80 years. I also mentioned search for better solutions. This may be prompted by crises, but it may be prompted by markets desperately trying to make more profit. After all, Tesla's done a pretty good job of breaking up the car market worldwide. But it may also be a matter of government policy, where governments actually move in and say, hey folks, we need some better solutions here, for example, to address issues such as climate change or declining international competitiveness. A further point I'd like to make is, in case any of you think this is a story of the survival of the fittest, it isn't. Technical solutions are seldom neat and very often imperfect. They are, in short, it is, if you like, the survival of the adequate. Okay? I don't wish to wind Vaughan up, but electric cars don't perform very well in cold weather. Nuclear was seen as being too cheap to meter, but clearly no one thought about nuclear waste. So what I'm suggesting is there's nothing perfect or optimal about the technology that emerges from an evolutionary process. It just does the job. It is satisfactory rather than optimal. And finally, I mentioned that ideas change and adapt as they spread in an emergent way. And that's often because users are dissatisfied with the technical solution, often because users think of smarter ways of using a mobile phone, like text messaging, which was actually added as an afterthought to help the operators, not as a consumer gimmick. So it's often the case that this emergence of new technologies is partly driven by consumers. Okay, let me tell you about one of the loves of my life. It's totally irrational. It's given me, as I said, much work and trouble. That is, I would like to look at one of my favourite technologies, the 130-year-old history of the wide strip mill for rolling steel. Some of you, of course, saw this at the annual Newcomen annual tour at Port Talbot. It's actually another South Wales strip mill. It's a painting of a mill at Land Road. 60 years ago, these were prestige items, and people would commission paintings of their mill to proudly display in the boardroom. How things have changed. Okay, I want to talk about Wittgenstein's dad. Wittgenstein, as some of you may know, is one of our most famous members of staff at the University of Manchester, or at least at UMIS, where he was a would-be aeronautical engineer. This is not Ludwig Wittgenstein, this is Carl Wittgenstein, his dad, that we want to talk about. I'm going to talk about the emergence of various technical solutions and point out that a crisis in automobile production actually prompted a search for competing solutions to solve this problem of rolling wide body sheet for car bodies. A dominant design emerged by about 1930, and frankly, it hasn't changed much since. For the last 90 years, we've been doing much the same thing. There have been attempts to improve it. I'll outline those. There have been attempts to circumvent it, which have failed. That's the generation of variety for you. But essentially, the technology has been locked in for 90 years. So the story of evolution gives you an insight into how this technology has both developed and not developed. Okay, let's talk about Wittgenstein's dad. Wittgenstein's dad was very wealthy because he had essentially what amounted to monopoly control of the steel supply of the Austro-Habsburg Empire. He was the leader of the cartel, and so he had plenty of money to pay with. And this is a mill that was built in his firm at Techlets. Now, Techlets is an interesting place because it shifts from country to country. So much so that you can tell when the article is written by which country it puts it in. When I looked it up last night, it had moved to Germany. But there you go. It was in, as I recall, Czechoslovakia. What was subsequently Czechoslovakia is now the Czech Republic. It was built in 1892 and abandoned in 1907. Why was it abandoned? Excuse me. It had all the principles of a modern strip mill, if you like. Working the vertical section was the roughing down of ingots to plates or semi-finished products, and then it rolled to the right to go through the finishing train. There's a simple problem that anyone who's an engineer will recognise: a mass flow. As something gets rolled thinner, it has to roll faster, otherwise it will accumulate between the stands. And as you can see from this drawing, powered by a steam engine at the top of the diagram, all the mills are geared together so they can only operate on one relative, all the stands must operate in the same relative speed ratio. So a thicker product is going to be stretched out, and a thinner product is going to accumulate between the stands. Perhaps they didn't understand the principle of mass flow when they designed it, but basically they abandoned it. And there were a variety of technical solutions that were pursued. There's one that's been discussed, for instance, on the Newcomen website with regard to Timplate Mills, which was to have a single stand and a large amount of manual labour. This is actually cold rolling of steel sheets, probably actually for car bodies in the 1920s at Shotton. But it was incredibly labour intensive, horrible, heavy, dirty work, even by the standards of the 1920s in America. It was short of labour. It was very labour intensive. It was very inefficient in terms of yield and produced lousy quality, uneven gauge, and not particularly flat material, hardly ideal for making a car body. There was another solution, which was to roll very narrow strip. This is a mill at Sharon Steel, which was built in 1920. This is just the sort of front end of it. Was to roll narrow strip. You may ask, why couldn't they roll wider strip continuously? And the answer is, apart from the mass flow problem, friction. The friction goes up as the rolling load goes up. So as you roll wider strip, the friction load is quite absurd, and the power just wasn't there to roll the wider strip. And in practice, what happened was that technical progress in this knotty problem of rolling wide sheets of steel was going nowhere during the 1920s. But as evolutionary theory would suggest, come a crisis, comes a solution. The crisis was what Thomas Hughes has called a reverse salient. People were searching for ways in which to increase the supply of automobiles for the 1920s American market, which was exploding after the First World War with growing affluence and the improvements in the road system. This is a genuine photo of General Motors about the early 1920s, which I discovered at Fordham University on a blizzard swept day. And you can see the two remarkable features of this. Firstly, the car body is made of wood. It's essentially a stagecoach on rubber wheels with an engine. There is, though, if you'll see, a sheet steel bonnet there at the front. And the other remarkable feature is they're using the latest in handheld power tools. So they weren't afraid to innovate, they just didn't have the ability to make the bodies in the necessary volume. The unsung hero of all this is Edward Gowan Bud. Joe Ludwinka was his mate, and they had staged a breakthrough in the 1920s by using Bramah and Naismith's press technology, they showed that you could actually press out all steel car bodies. There used to be, so legend has it, a wonderful marketing term whereby they would drive a Dodge and a Ford Model T off a cliff. When they reached the bottom, the Dodge would drive off and the Ford Model T would be matchsticks. A rather impressive demonstration of the strengths and advantages of an all-steel car body. The central problem was they didn't have the steel. This was a crisis, as I say, a reverse salient that needed to be resolved. Variety comes into this. There were two solutions being pursued. The first one was to roll individual sheets in sequence on a line of stands, all in line. This was the idea of Techlets in a way. A chap called Bray had tried it at Monongahela and failed twice. You have to admire his tenacity. And Titus, the rather arrogant head of the American rolling mill company, Armco, started pursuing this, as we'll see, in 1924. There was also a couple of entrepreneurs, Gene Townsend and Harry Norgel, who might be called serial entrepreneurs in modern jargon, because they had already succeeded in making pressed steel parts for construction and were later to move on to all sorts of other innovations. And they instead wanted to pursue the idea of a wide continuous mill, which of course everyone told them you couldn't do because of friction. So here we have a rather dramatic picture from the Hagley archives of Ashland. No doubt that's Titus looking handsome on the left, tall, dark, tall, blonde and handsome. And as you can see, they're rolling individual sheets with much heat and cooling, trying to control the gauge and generally looking pretty pleased with themselves. That was the failure. On the other hand, there was an attempt by these two entrepreneurs at Columbia Steel Butler to make what was in practice the first continuous wide strip mill, a continuous flow process. The steel slab entered on the left, hot, and emerged on the right as a coil. This had so many innovations, it's a bit breathtaking really. It makes modern innovators look a bit dull. They solved 4 or 5 technical problems all in one fell swoop. They solved the friction problem by using roller bearings, particularly on the backup rolls, which could be bigger, but the smaller ones had to be, the work rolls had to be small to give a bite against steel, but the bigger ones could afford to be bigger. They supported and took all the separating force, all the thrust upwards and downwards on the bearings. They put roller bearings in place. They solved the flatness problem by using these 4 high stands, as we'll see in a moment. They coordinated this, solved the mass flow problem. They coordinated the rolling stands by using a technique from lifts and from mining called Wardlander controls. And just to add to the number of innovations that they packed into one small plant for a £2 million bill, was that they developed product handling, a logistics innovation using coils. Now, as I've said, friction absorbs power. This is an exhibit from Swansea Maritime Museum. It's the Timplate single stand mill, and you can see there glowing in the middle like gold is a brass bearing. Incredibly inefficient on lots of counts, lots of friction. You have to stop the mill to keep on lubricating it with something like pork fat. And what's more, the rolling mills, places like Shotton, used to have brass foundries in order to keep resupplying these bearings that soon wore down. You can see now why you couldn't roll wide strip, because the friction inherent in it was just too great and the friction losses were too great. What did Townsend and Norgel do? They went and spoke to one of the most famous Jewish American engineers of his time. According to his grandson, he was the second highest paid engineer in America at the time. I don't know how true that is. They went to spoke to William Messenger of the Hydraulic Tool Company, who had a really nice line in developing roller bearings. roller bearings, so they decided that they would put on roller bearings and thrust bearings onto the rolls to reduce the friction. And they also, to couple that with 4 high rolling stands, which had been developed by United Engineering for Rome, brass and copper. 4 high stands are able with the big bearings to go on the backup rolls, as you can see from this photo of the stand out in the weather of Ebbw Vale. The backup again meant you got much flatter strip because the work rolls didn't deflect, and the load was transferred to the bigger necks of the backup rolls. All round a great idea, and that had been developed by United Engineering Company for Rome, brass and copper. It's much easier to experiment with brass and copper because it's softer, lower temperatures. And one Colonel Bigot did a lot of the help with a lot of the development work. Now the point is about, and yes, Wardlander controls. For those of you who are perhaps very familiar with this, what you do is you have a series of electric motors seen here on the right, which take alternating current and generate direct current for the mill drive motors on the left, and it's much easier to control the speed of DC motors, or it was in those days for power chips. It was much easier to control the speed of DC motors. This is the Wardlander controls at Shotton. It's rumoured there are still some left at Scunthorpe, but I've not seen them. But other than that, they've now given way to direct digitally drive AC motors, but that's the way things go. And just to cap this sequence of innovations, they decided that coils, which are now ubiquitous, would be a much better way of handling things than sheets of strip. And this led on to coils being used for pickling, for cold rolling, for annealing, and so on. And that led to the continuous wide strip mill as we know it. This is a drawing of Shotton, and you can see that the material starts on the left-hand side as a thick slab and gets progressively rolled down into a thin coil, maybe a Butler up to about 3 tons, and nowadays 45 tons, and a thin coil of hot rolled material which is suitable for subsequent cold rolling. Now, what happened? We spoke about selection. Everyone in the technical press, everyone in the car industry who were their main customers, people in Timplate could all see that Townsend and Norgall's entrepreneurial efforts were by far and away the best solution. That was the selection environment, the market. What happened? Armco bought out Butler because their own experiments were pathetic and failed, and so they put a brave face on it. But they bought out Columbia Steel at Butler. They paid $20 million. Right? Townsend and Norgall had spent $2 million developing the technology. They didn't get all the profit. They only got $2 million out of it because the Mellon Bank had funded a large amount of the development. But nevertheless, they did pretty nicely, thank you very much. And as you can see, they went on a millionaire's holiday around the world and agreed never to compete with Armco again. They went off and actually worked on the development of bearing steels because they were just compulsive innovators, as the pair of. Okay, so that's both an unsung American story and also shows you the way in which, in this case, a crisis had prompted a variety of solutions and a selection mechanism from the market, and this brought innovation. Now, of course, you'd like it to be a good news story all along, but it isn't. Because actually, frankly, very little has happened since. From 1926 onwards, helped by United, of course, who'd done the 4 high stand development and encouraged Townsend and Norgall to experiment with bearings, this collaborative group, United, did very well and sold mills around the world, right up until Marshall Aid and afterwards. And by the 1960s, there was growing pressure from post-war economic expansion and Europe and Japan, and also post-war growth in the United States, led to much larger mills with heavier coil weights, with bigger slabs, of course, to make the heavier coils, and computer control, and Generation 2 emerged. By the 1970s, this had reached the heights of absurdity, and just in time for the first oil crisis of 1974-75, huge energy-guzzling Generation 3 mills pursued the search for economies of scale just at exactly the wrong moment. By the 1980s, people realized that these mills were much too expensive, and various attempts were made to cut back the capital outlays. And then some clever Germans thought, well, look, we could actually obviate the roughing stand by casting thin slabs, which allowed low output mills and the entry of the mini mill sector. But frankly, nearly all of that is just incremental change. And in the last 30 years, apart from one or two innovative mills in places like Cremona in Italy, nothing has come of development. Like paper mills have stuck in time, wide hot strip mills are stuck in time. So the point that I'm trying to make is that evolution implies not only that things change, but also that things don't change. All right, you can actually get, and this is the phrase that people use, you can actually get locked into a technology and it can become stagnant and dormant, seeing very little innovation, as everyone thinks that the present one is doing a perfectly satisfactory job. So let's draw some lessons from all of this. The variety of approach, Armco versus these entrepreneurs at Columbia Steel, Butler, brought failure as well as success. That is the nature of the market system. That is the nature of technical innovation, that you get failure as well as success. In this case, Armco were rich enough to buy out the success. But certainly as a result of that, there was extinction of all the hand mills, although I think the last Timplate Mills probably hung on in South Wales till the mid-1950s. It's interesting that variety was prompted by people desperately searching for a solution. The crisis of auto body sheet induced a radical search for change, and it was very successful. The price of steel strip halved in about 10 years between the late 1920s and the late 1930s. The gauge was much better. You could have big American cars with wide roofs and big hoods, big bonnets as they call them, and big bonnets as we call them. You could have the American dream. In fact, I think I said in that article, it was the magic carpet ride of the American dream was the large automobile, unlocked by the development of the wide strip. But this radical innovation didn't continue, because once we've got a satisfactory solution, we got locked into a dominant design, and there was only incremental change for a century. In fact, I'm looking forward to the century of the wide strip mill. It will give me an excuse to publish some articles in America saying, you've ignored this history. By the way, it's a century old. By the way, isn't it about time someone did some innovating? It's true that the design has been modified as technical leadership moved around the world, first of all from America to Europe in terms of design, some input from Japan, and still actually technical leadership probably resides in Europe, particularly in Italy at the moment. Okay, I'm running out of time, so I just want to say, I won't get on to policy, but I just want to say some very surprising things about what we can talk about in terms of evolution in technology as opposed to biology. First of all, this is not biological evolution. It's just that the biologists got there first with evolution. Evolution is quite a general, generic principle which applies across a range of technology, a range of fields. It doesn't necessarily apply just to biology. And it isn't the same as biology. For a start, there's Maureen McKelvey, the Swedish evolutionary economists often saying, there's a strong element of purposive selection. Entrepreneurs make sensible choices as to what route to pursue. This is not random like Darwinian evolution, and there's a strong element of selection by the market afterwards. Again, it's not survival of the fittest. If you think about it, technical evolution hasn't got that long. Darwinian processes are largely random and take millions of years. We want solutions to climate change now, please. Okay, there's no comparison between the two. Nor can you say it's the survival of the fittest, it's more the survival of the suitable. That'll do, that's a solution. We'll pursue that. We know it's not the ideal nuclear reactor, but it'll do. Thirdly, this isn't like an biological environment. The selection environment amongst humans, in society, in a modern economy, is always changing. There are shifts in taste and demand. Lots of complementary technologies are changing. We've heard about power chips making AC drives plausible, for instance. There are changes in relative prices that make something sensible now that weren't sensible before. There are growths in alternative technologies which might compete for people's leisure time, for example. And there is chance in this. There is chance. If Townsend hadn't met Norval, what would have happened? Would we have had the continuous wide strip mill? It's chance, but it's not random chance in the way that Darwinian processes are random. Humans copy and learn from one another. And Eldridge once said somewhere like, natural environments do not indulge in industrial espionage. Okay? If there's no evidence that Darwin's finches copied one another in the way that, for example, we've seen in that strip mills paper that the Germans ripped off the Americans before the Second World War in developing strip mills. They just copied things. They just ripped them off. Stop. It was just straightforward theft. Okay, so we're not actually talking about Charles Darwin. We're talking about a Frenchman who got closer to the higher idea of evolution, who is Jean-Baptiste Pierre Antoine de Monet de Lamarck, Jean Lamarck to you. 50 years before Darwin, he was writing on evolution, and he said a great deal of strange things. This is Jean Lamarck, who got dotage on his fourth marriage, going blind, and a member of the Institut Français, very esteemed, but he wasn't always esteemed, particularly in his youth, and was prone to weep when his ideas weren't taken up. Among the very many points in this rather strange book that he wrote on evolution 50 years before Darwin was that he thought that evolution was almost an inevitable process. He said if the environment changes, the species will change, which is far more deterministic than Darwin ever was. He'd obviously never seen a coelacanth for a start, which hasn't changed one jot in however many 300 and something million years. He also believed, which is completely contrary to what we all know about modern genetics, is that acquired characteristics will be directly inherited. But that's precisely what happens in the technological realm. If you see a better idea, you copy it, or you work around it, or you imitate it, or you try and find an alternative. This is direct inheritance. That's how technology evolves, not how biology evolves. And finally, he had this curious idea that evolution would always move towards complexity. It would go from slugs to humans, if you like. More controversial, those of you who wrestled with a modern mobile phone will probably think, well, that's a pretty fair insight. So Darwin believed in chance mutation over millions of years, genetic drift, gradual natural selection. That's the model we pursue in biology. Lamarck had a metaphysical belief. It was almost like not a religion, but he certainly believed in progression from worms to humans. And he said that redundant characteristics will die out, but of course they don't. Most of us have appendices left in us. Okay. Now, to sum up, what about some of the criticisms? Otto Meyer, who's famous as the head of the Deutsche Museum in the 90s, roundly lambasted the idea of evolution and technology and culture 30 years ago. He said the trouble with evolutionary models is that they're incapable of dealing with two of the most interesting problems in the history of technology. The creative process that produces new technology, in other words, he wanted to know about inventors. He wasn't particularly interested in the spread of technology, he wanted to know about inventors. And he wanted to know something about the decision-making process by which society decides what to do with newly available technologies. He wanted history with heroes. Now, I can understand that. There's nothing like getting dug in, as some of you know. My current hero is Ludwig Lervius, the exiled engineer from Germany. There's nothing like a good hero to dig into. But of course, the reality of much technical development is that it's carried out in teams by huge numbers of largely anonymous people and coders, and it's a wide variety of people, and as multiple independent inventions often show, lots of people come to the same conclusion at the same time. So I'm not writing off heroes. They're great fun to write about and even greater fun to read about. That is to miss what we're actually trying to do in the history of technology. And finally, I'm going to stop at this point and emphasize something that is very much neglected in the history of technology. We focus on inventors and innovators. We actually say remarkably little about entrepreneurs. There are few articles in the journal about entrepreneurial success stories, people who made their money and went away on holiday around the world. Townsend and Norval were experienced innovators. They had a rash of patents on things like gutters and drains and fixings for things, all made of steel. They were experienced innovators. They had a hunch that they could improve the wide strip, they could improve strip rolling, and they did calculated guesswork and talked to an enormous number of people. They must have had immense charm to gather together this wide range of collaborators, from United to Westinghouse to Messenger. So, So I think we need to think about, need to think about more about entrepreneurs, and point out that quite often it is the case when we're developing new technologies that they often combine existing technologies. There are numerous papers in the journal on subjects ranging, for instance, from the V2 rocket to the example that I've just given you about wide strip mills. Well, the technologies were there, it just needed someone with the nous to pull them all together in a way that makes profits and gets selected by the market. And finally, one point about the entrepreneur is that the knowledge was already out there, as I've just suggested. The role of the entrepreneur, Townsend and Norval, was to have the genius to put it all together. So the knowledge was widely distributed. They brought it into focus. In practice, they didn't actually invent anything. They just had the nous to put it all together and adopt it. Okay, I'm not going to talk about policy. Instead, I'm just going to sum up and say what lessons can be learned. The first one is, I think, that complex evolutionary systems are continually exploring, experimenting, but can stop that when they get locked into a prevailing trajectory or prevailing technology. Secondly, that we don't have a clue where we're heading. All we know is that some firms will rise and some will fall. Those of you who have stock market portfolios are bitterly aware of this, of course, and this implies not just the rise and fall of firms, but industries, nations, and whole communities. Of course, part of the lesson of this is that we need to allow new technologies to emerge and let them enter the market. So what we need to focus on for technology policy is to make sure that new things are not restricted by existing incumbents saying this is how we've always done it, and we've got a nice little niche here making large profits, and we don't want you to come and trespass. Thank you very much. You want the competition policy focuses on entry. And you've got to recognise that locked-in technologies can stagnate, and that if you're going to get rid of them and replace them with something else, you may need to help local communities and workers adjust to their departure. Okay, I'm going to stop at that point because my hour is up, and invite questions, outrage, and disagreement. Thank you, Dawn. Thank you, Jonathan. That makes you do things. I found that while briefing. Frank, start us off, was it?
Think away, and with any luck. I'll repeat that. Thank you, Jonathan. That was super, and I'm glad you chose Lamarck as your evolutionary network rather than Darwin for the reasons you outlined. So, a comment on the question. The comment is that Darwin's grandfather, Baptist Darwin, living slightly before Lamarck, also developed a theory of evolution without any explanatory framework. And the question is a metaphor that comes from Darwin rather than Lamarck, and that is of biogeographical distribution being a major driver of evolutionary change. And you imply that a bit in some of your examples of certain knowledge being located in certain countries, which in the sort of 1920s and 30s have been far more isolated and hard to get at. And I wonder if you sort of think about possibly, I'm not expecting a definitive answer, I just wonder if you think, when you come to write this paper for the journal, if you think about the biogeographical metaphor in the transmission of knowledge and development of knowledge within a particular knowledge community, which is then passed out to another knowledge community, which may have been developing along further lines. And that is a Darwinian idea.
Thank you, Frank. I'll plagiarise that shamelessly. You're dead right, and one can point to clusters of knowledge in particular locations even today. One of my favourites, in fact, it would perhaps make a better lecture, is the Formula One cluster of Motorsport Valley around the most unlikely locations in Oxfordshire, Northamptonshire, Milton Keynes, for goodness sake, where you see specific knowledge relating to high performance racing cars being located within a radius of about 50 or 100 miles in Britain. Why is it virtually every single Formula One car in the world is built in that area? Why do Mercedes build in Milton Keynes? You have to go to great lengths to find exceptions, perhaps Ferrari, I suppose, partly building in Italy. And you can't help avoiding that there are important locational factors that cause knowledge to cluster. In that case, it's probably engineers moving from team to team, going to the pub together after work, having nice houses, inviting one another over to dinner on Saturday night. It's the fact that the gearbox firms and the component suppliers and the electronics know-how and the aerospace testing are all clustered in close hand. But it has to, as you suggest, have a spatial element. And one of the things that I tried to do was to try and sort out the addresses of people that helped Columbia Steel develop. And they were all closely clustered around Ohio and Pennsylvania. It's quite clear that they knew one another. There's also a religious theme here, which that William Messenger was quite clearly Jewish. He's funded the synagogue. United Engineering were less Orthodox Jews, but were nevertheless Jewish. I don't know about Townsend and Norgal, because despite their fame, in my view, there's relatively little known about them, even in their hometowns. But I suspect there was a cluster of financiers and technical know-how in complementary technologies, so that's bearings, mill design, banking in the Mellon case, who were in Pittsburgh, again leading to a geographical cluster. And one wonders whether the wide hot strip mill would have been developed anywhere else in the world. Possibly Germany, perhaps, but I don't think that these spatial factors are critical. So I think you're dead right, and I shall borrow that idea. Thank you very much. Down there. Yeah. Hi, Peter. Are you there? Peter Turvey?
Yeah, I'm here. Yeah.
Ah, right. There you are. I've just asked you to unmute, and you seem to have done it. So ask your question.
Yeah.
You had a question to ask, did you, Peter?
Sorry?
You had a question to ask, did you?
Yes, it was about steam submarines. I know they were assumed that they were a write-off, but actually the key innovation there was the adoption of nuclear power as a heat source for steam propulsion. So it's so interesting. Another would you regard this as another little evolutionary mechanism? A lot of things lying dormant, waiting for that extra jerk kick idea to make them practical.
Well, yes, there's nothing like reinventing an old idea to make some money, is there?
Yeah, that's true.
I mean, the idea of dousing a coal-fired boiler before you dive and making sure that all the relevant funnels are locked away and waterproof is mildly absurd. And you're dead right. It reached its what's the word, apotheosis with the nuclear submarine, which are of course by steam turbines of a relatively low temperature. I guess they could be more efficient at a higher temperature, but you wouldn't necessarily want that on a submarine. The higher temperature would have been on the old steam-fired coal fired.
Yes. Yeah. Okay. Thank you. Thank you.
Right.
I have a lot to disagree with.
Right.
But my principal disagreement is that it's written from the point of view of somebody who hasn't actually worked in technological research. You don't realize that although there might be teams putting things together which gradually develop as the idea starts, the idea starts with one person. That's how it works. And it develops from that. I've seen it from my own point of view, and quite often that person gets lost eventually. British Gas is actually a very good organisation for seeing such a process at work. British Gas was a dying industry in the 1950s, and yet all through the industry, innovation began. And I don't know who started these bits. Steam reforming, better gas cookers, much improved gas fires, central heating. All of these came about, long distance pipelines. They suddenly appeared all at once and kept British Gas alive. So as somebody said to me this evening,
Oh yes, wind power is supplying more than 50% of the energy, of the electricity at the moment. But it's trivial when you look at how much gas is used in the economy. And all of this came about through the development in a nationalized industry, which was regarded as being very, very sluggish and backward. And yet it's the dominant force in the economy now. You need to look at how these individuals got to work and the way that the company as a whole encouraged such people and allowed them to form teams.
Okay, Fred, I shall shock you. One of the possibilities for looking at variety and selection was actually the production of gas during the 60s and 70s that you have documented in your papers. And because here was a great example of a wide variety of technical solutions being pursued, and as you've explained in your papers, there was some attempt to select out the best technologies for making artificial town gas. Now, that was an evolutionary process that was truncated by the discovery of large amounts of North Sea gas, although some of it, you'll probably say, went on afterwards in ICI. So I agree wholeheartedly with what you say about variety and selection in gas. It's a brilliant example. And that's also a brilliant example of crisis prompting a search for a solution. Because the gas industry, as again you've explained, was in terminal decline, relying on gasification of coke. It was very much an obsolete industry with an obsolete capital stock, which had lots of undesirable characteristics. It was seen as smelly, for example. So I think you're right. I have a rather embarrassing confession to make. I have spent time working in innovation, and I'm embarrassed to say I was once a member of a team that received the prize for it in the food industry. So I do concur with you that when it gets to the brainstorming stage of what the hell are we going to do to keep this company on Sainsbury's shelves, you do often rely upon a bright idea coming up that the team pursues. And I don't want to say, by pursuing the analogy of innovation, that invention doesn't matter, or more to the point, entrepreneurs don't matter. And you get entrepreneurs within even organizations. And I certainly don't believe that nationalized industries are poor at innovation, because I've been going around the country saying how remarkably progressive British Rail was in the 1970s to everyone's disbelief. So I agree with you. Actually, I agree with you wholeheartedly. And if you give me the references, I'll gladly mention that in the paper. Thank you. Yeah. This is just a thought. The strip may or may not have changed, but has the product coming off the end changed? Because we've done a lot of things with design of steel. I remember doing the reactors for sizable things. Where do you get the reinforcing from? The reinforcings from Japan Steelworks, and Japan Steelworks were using the rolls that were put in by Armstrongs for rolling battleship armour. Now, that was the big place where you could do these very big ring forgings, but the material that was coming out was quite different to what the rolls were originally put there for. So if you look at the whole innovation process, there's the manufacturing method, machine tools, whatever, may not have changed, but the product coming out at the end may be very different. So the question is, the hammer may be the same, the thing you make may be completely different. I'm not sure that just because the strip mill hasn't moved on, we haven't moved on the technology quite considerably as to what comes out the end. I don't think the steel we put in a car these days is necessarily the same as before used. And when you move on to what we're now putting in the car, it's predominantly aluminium. My experience was one of the problems with an aluminium mill was the rate at which they have fires during production. several times a day on the soil plant. To go through carbon dioxide like there's no tomorrow, trying to control them. And by the way, an electric car is very good in cold weather. It's brilliant on snow and ice. Yeah. That's control. I can't comment on electric cars, but you have a very good point. There is no doubt that I have focused here on process innovation and not mentioned product innovation. And you're right to say that the new generations of high strength, low alloy steels are made much more cheaply, are made much thinner, have better welding properties, although Bob Bowden might disagree with that, have better welding properties and are much lighter in weight, and have also now been coated for corrosion resistance. So there has been a continual evolution in the product being made. In that sense, you are correct. Although many would regard that as evolution as incremental rather than anything radical. Yeah, you've got a good point there. Yeah, thank you.
Any more contributions online? Richard Williams has a point to make. Yeah, do you want to flip Richard on? Richard Williams has a point to make, has he?
Yeah. Can you hear me?
Yeah.
I simply made the point that it's very difficult to know sometimes, particularly if you go back in history, as to who was the entrepreneur and who was the inventor. And I just cited the example of Darby the First, who was, as everybody has claimed for many years, quite wrongly, was the first man to smelt iron with coke. In fact, the guy that did that was not Abraham Darby at all. He was certainly the guy that used it, and certainly the guy that got fame and money out of it. The guy that actually did it for him, Abraham Darby had never run a blast furnace in his life beforehand, but the guy that did it for him was a chap by the name of John Tyler. And I don't know how many people have heard of this John Tyler, but he was the furnace man. And he had done exactly the same job for Shadrach Fox in the 1690s, and heavens knows, where at exactly what stage he did it. But so was John Wilkinson, for example, another steel man, iron man, was he an inventor or an entrepreneur? We say he was the first to do this, but was it his idea or somebody else's?
I agree that invention has many fathers. If you look at something familiar like the history of the steam engine, you can point to this invention and that invention that went to make a more efficient thing. Brian Arthur, the evolutionary economist, often says that there's no point in assigning invention to any one person because of these multiple contributions. To go back to what Fred Starr has just been saying, what matters is the team that brings it to market and brings it as a profitable opportunity and sees it through the struggle and the sweat and picks up on the bright idea and actually makes it into a viable commercial technology. And I think that Brian Arthur has a very good point, and that's a quote from the beginning of my Bloodhound article, that it's the team that matters. And I agree that this search for heroes, nevertheless, is a very romantic one, and I guess we all want our heroes, and it's quite natural to look for them.
Some of us want to be heroes.
Okay, any questions at all? David?
Yes, I'd like to just question about the role of what might come before the technology, which is the science. That is often much more of a serendipitous nature, particularly if you look at the pharmaceutical or the biopharmaceutical industries. Drugs are often discovered quite by chance. We've got an example in the news only today for Parkinson's disease. It wasn't designed to be like that, but it has come out to be like that. And we saw it in COVID with the team in Oxford, just examining outpatients with being treated with other things. They're actually responding. there's a lot of science that's got to come there, maybe even in metallurgy. It's the metallurgy that actually might be moving things forward rather than the technology, machine design.
Okay. Now, that's the subject for at least 2 more lectures. One lecture would be, does the evolutionary model apply to science? And I wouldn't dream of going there. Other people have. The second issue is whether there's actually much relationship between science and technology. You pick pharmaceutical examples, and indeed, one of the best books on the evolution of technology is Maureen McKelvey's book on looking at biotech, particularly in Sweden. But for the most part, the work that I've certainly published, I find very little, if any, connection between science and technology. I certainly don't believe in the linear model that research leads to productive science, which gets commercialized into technology. And the most compelling example, going back to the steam engine, is of course that thermodynamics didn't turn up until the steam engine had been going about 200 and something years, and actually had very little influence on the reciprocating steam engine. You can point to uniflow engines, I guess, but for the most part, it was suck it and see. And going back to Fred's point, my limited experience as a practical innovator at UMIS for about 6 or 7 years was it was very much suck it and see. And in the examples that I've given you, whether it was a Bloodhound, whether it was the White Hot Strip Mill, had very little to do with science as we would understand it. And even in the development of the atom bomb, which I promised myself I wouldn't mention tonight, even in the development of nuclear weapons, what was astonishing in the research that I did there was the fact that it was largely about engineering, practical problem solving, mundane difficulties with potting electric circuits, with cutting explosives with saws using vacuum cleaners to take the dust away. It was about practical, down-to-earth, everyday tinkering, cussing, swearing, making mistakes, fortunately none of them fatal, and very little to do with science. And as we were discussing before we came here today, most sixth formers could manage the science, and I suspect quite a few do in the backs of chemistry labs when their teachers are concentrating on the SWATs in the front. Making a nuclear weapon is remarkably unscientific. It is a huge engineering challenge of a vast order. So I haven't mentioned science tonight. I've got it off my chest now as to why I haven't mentioned science, but actually I think there's very little to do, very little connection between science and technology. Sure, it's one of the inputs, but then so is good bearings technology, an understanding of how to saw up explosives. Yeah.
Having said a lot to criticize in what you say, and I agree with you to a degree. And one of the best examples we have of science not being involved in doing something is the Wright flyer. The Wright brothers, the Wright produced the first successful aeroplane. It was astounding in what it could do, how it could fly. But what the Wright brothers did, they had a scientific attitude to the way that they put things together. They designed a wind tunnel. They saw that, well, the figures for lift and drag that they were getting from Lilienthal were rubbish. They got better figures. They went out and built a kite, not a glider. They found out how to control the kite. All these were the scientific ways of doing things. And I'm quite sure that when you were concocting some food that probably poisoned us, Um, in about 20 years later, maybe even 70 years later, you had a scientific way of doing the job. And that's the thing that science teaches technology, a rational way to approach problems.
Yeah, and I do think the discipline of mathematics, for a start, you're not going to get far as an engineer if you've not got good maths. So maths and science, I would agree with that. But I don't believe, I mean, there are some glorious instances of people saying engineers ought to go and observe scientists in their labs. I actually think scientists ought to go and observe what engineers do, and that would produce more of a symbiosis. It's a complicated one. There are clearly examples where you can point to science breakthroughs leading to innovation. But if I was advising the government on innovation policy, I wouldn't think that stacking up science is the best route to it.
Yeah. When we get the book written up, Jonathan, you can add all this stuff in the back of it. Not sure I quite go with that, but I think there is a fundamental difference between designing engineered products and designing the way you produce them. And I think that's possibly an area where this needs a bit of thinking, because you can retain the production method. Hammers, chisels, screwdrivers still work quite well. Can't do an awful lot to improve them. But the way you use them and what you turn out at the end, and also the change in the way we use prototype. There's an awful lot more prototyping that's done, computational, etc. Greater confidence. We don't necessarily fly 2, 3, 4 prototypes of an aeroplane before you put it into service. You should do maybe, but and there's a shift towards the way that innovation is heading towards control technologies and things which allow you to do things you wouldn't dream doing before. Anyway, any further questions? One fast question, Frank, come on.
Talking about the science engineering nexus relationship. I mean, I agree with you entirely, Jonathan, that until probably about 1850, most of the industrialization happened up until that point could have happened without knowing inverse square law, gravitation, or like was composed of 7 colors, allegedly. Yes, that's believed that. But I think from 1850 onwards, scientific method. How much closer do you want to get? I'm facing the microphone. Scientific knowledge, scientific method becomes increasingly important in providing the knowledge base and some of the rationality, to use Fred's phrase, of engineering practice. What is then interesting is why you get this mindless linear model, which people like politicians and journalists believe in. I mean, it's quite extraordinary. I mean, for various reasons, I was reading the Realizing Our Potential white paper from 1993 yesterday, and it's embedded there. There is some value in science, as David's pointed out with pharmaceuticals, but I mean, it's look, if you look at the Davy lamp, which is something I've looked at it quite closely, there's no science in it. I mean, but Davy claims it was scientific, and I think the really interesting historical question is, why do people keep on making these claims about something happening in the laboratory, thereby having huge impact outside in terms of scientific application? And I think that's a really worthwhile question, because if that's the question that actually influences politicians and policymakers and journalists and all those sort of people who don't actually understand what they're talking about.
I think we'll probably call it draw stumps now. You look as if you've probably done enough thinking for the evening. We probably have too. So thank you very much, Jonathan. Let's thank you in the usual way. And before we all break up, and for those online, the next meeting held here in the gallery will be on the 8th of February. It will be given by Drs. John Konevsky and Mark Pegg. It will be entitled Mechanisation of the British Coal Industry. And given the papers we've heard recently from John, this is relatively recent. This is the rise and fall of the coal industry was one of the key drivers of Britain's industrial, technological and economic history for over 3 centuries. The increasing mechanisation under nationalised industry after World War II and the managed retreat from large-scale coal mining presents a fascinating study in the history of engineering and technology. So it sort of follows on quite well, John, because that change in terms of how a nationalised industry innovated and took us into very much mechanised coal mining, and that research, of course, fell apart with the breakup of the coal board, as did a lot of the other centralised research facilities of the electricity supply industry and so forth. So that could be quite an interesting evening. That's 8th of February, and join us either online or here if you wish. We've got a large audience here, probably the largest we've had so far. It's been gradually growing during the lecture. So thank you all very much, and safe journey home for those who have got to travel, and for those who are sitting at home, have a pleasant evening. Thank you all.